Good afternoon, everyone. It's great honor to share my research here. I'm Dongxing from Hunan University, China. The title of my presentation is Rapid Prediction of Hand Cycle Fatigue Purpose of Hand Entropy Errors based on Sleeper Invisibility Localization. There are five parts to my presentation. Let's start with the introduction first. Okay, in recent years, hand entropy errors has become a major research focus in advanced errors materials. Thanks to their unique design concept and excellent mechanical properties, the chemical complexities, however, pose a considerable difficulty in evaluating mechanical properties, especially fatigue properties. As we know, because fatigue properties of HEAS vary significant with elemental radius. So, therefore, developing a fast and feasible evaluation method has become a key research issue. Um, to address these issues, multi-scale simulation methods serve as effective methods made for studying HEA fatigue behavior. We know the fatigue nucleation in metallic materials stem from localized microstructures. So the microscale simulations provide the crucial insights into damaging features and their evolution. There are exactly the key informations for unraveling fatigue mechanism. As fatigue mechanism is critical for reliable evaluation. Therefore, this study aims to develop a method for fatigue damage evaluation and fatigue strength prediction based on microscale simulation. At first, the key to establish a reliable fatigue prediction mode lies in propose effective fatigue indicator parameter, namely FIP. This FIP should reflect the intrinsic characteristic of fatigue. Um, Prior study in science has identified sleeper inversibility as the intrinsic FIP for evaluator errors fatigue properties. However, cyclical sleep localization is another critical intrinsic characteristic because it drives stress concentration and accelerates fatigue correct initiation. As highlighted on the slide, it is necessary to focus on the important factor of localization of cyclical sleeper in fatigue evaluation model. At first, we proposed the approach that comprehensively considers two core characteristics of cyclical sleeper, namely sleeper inversibility and sleeper localization. To construct this particular indicator parameter, we integrate two key fatigue features, the inversible accumulation of shear strength and the degree of cyclical deformation localizations. To capture this localization factor, we adopt a specially partitioned strategy. And then we couple the two intrinsic characteristics of fatigue through a reasonable framework, as shown in this function. The study used in this stage are typically equal KFNs hand entropy errors with a variable alumina and nickel contents, including four representative compositions as shown in the table. We construct and variety respective rooms in elements REEs for these four materials, as shown in the figure. Then we perform a cyclical loading use the MD simulations to quantitative measure and analyze the sleeper inversibilities localization. Moving to the results of the discussions, we first observe that the compositional changes has a significant impact on the cyclical sleeper characteristics of HEA. For example, uh, they show the two ions compared ions with aluminum to nickel radiations of Z port 1 and Z port 2. 0.3, sorry, as shown in the form Mrs. Strength counterparts, we can see even slight composition variations lead to marked difference in sleeper localization. Moreover, we also can say this difference in sleeper localizations are complex. To quantify this difference for evaluate the fatigue properties of HAEs with different compositions. The fatigue damages degrees of materials was evaluated based on the proposed FIP, namely W. Here we have two main findings. First, we can see in the left figure, the W of all study errors reach the standard stage at the initial stage of cyclical loading. Second, the W of four HEAs with different compositions are different, as shown in the right figure. This indicates that the proposed FIP is sensitive to the compositional changes. We further explore the source of difference in sleeper inversibility localization among the four HEAs. We focus on the two HEAs with the biggest W difference. These are the aluminum to nickel radiations of Z.1 and Z.3. It can be found in the figure that the deformation mechanism. This confirms that the deformation mechanism under cyclical loads are distinct. We can say the dislocation motion is characterized by dislocation tangles and exciting dislocations, respectively. This confirms that the dislocation behavior is highly sensitive to composition and microstructures, and we can see this sensitivity can transform effective to lead to our proposed FIP. So, as summarized in the figure, we outlined the main cyclical deformation mechanisms of the four HEA and the correlation with sleeper inversibility localization. We can see this change in deformation mechanisms leads to variation in the sleeper inversibility localization. These changes affect the damage accumulation rate and leads to difference in the fatigue resistance of this HEA. From the results above, our proposed FIP reflects the intrinsic difference of this HEA. So we can further explore its relationship with fatigue properties. By by comparing this four HEAs, this sleeper characterizations and the fatigue strength ratio of materials. It can be said in the table. We can see the run the non-sleeper inversibility localization W is respond to the hand fatigue stress relations. So therefore we building a correlations models between the W and the strength and fatigue strength relations. We can say this fund this fund. Finally, we use our model to predict the 4HES fatigue stress. The deviation between the prediction and the experimental date is within 12%. That's reliable. Compared to the traditional sleeper inversibility indicator P, our indicator Ws improve the prediction accuracy by si- oh, sorry, by by 36%, as shown in the left figure. In the right figure, in summary, our indicate W enable fatigue strength prediction for the 4HES with the variable compositions, provide a new methods for rapid prediction of HES fatigue properties. So some conclusions can be drawn out. We propose evaluation methods of fatigue properties based on sleeper inversibility localization. The effectiveness of this method in reflecting the relationship between the microstructural deformation and the fatigue resistance has been verified. This providing a feasible technical approach for the design of fatigue-resisting HEA. It's all about my presentation. Thank you for your attention.